Hello everyone, I hope that you are having an amazing day. This video is created by me and my team project assignment for MAA 111 course. The topic that we have chosen for the discussion is computer graphics. We are going to explore on how linear algebra is being implemented in this field. Before we begin, let's get to know all my group members first. The one on the left is me, Muhammad Zikri bin Rahmat. Next, the one on the middle is Amma Fahmi bin Muhammad Zaim, and our last group member, the one on the right, is Cheh Kit Hong. We all have evenly distributed our work for this assignment, and just stay tuned in this video for their part afterward. So let's begin. What is computer graphic? Computer graphic is the field of computer science that is concerned with the creation and manipulations of images and videos using computers. It encompasses a wide range of techniques including 2D and 3D graphics, animations, rendering, and visual effects. These techniques are used in a variety of applications such as video games, movies, and scientific visualization as well as user interfaces. This just shows on how significant are computer graphics in our life. So, how does linear algebra plays its role in this field? We are going to explore them furthermore later in the video when my teammate explain it to you. Next, for the chapter from our syllabus that was mainly used for this topic, it is chapter 6, which is the linear transformation. How? Well, we will get to that later on. As for the other topic in this course, they are also crucial for us to understand the basic of this whole vector, coordinate, and transforming stuff. They will surely help us to have a better understanding in our discussion. Next, we are going to explain what is a homogeneous coordinate as it is an important aspect for this field. Homogeneous coordinates are a way to represent points and vectors in a multi-dimensional space by using a single set of coordinates that have a fixed ratio. This also allows for a more elegant and unified mathematical treatment of geometric transformations such as translation, rotation, scaling, and many more. In a 2D space, a point x and y can be represented by the homogeneous coordinate x, y, and 1, while a vector xy can also be represented by the homogeneous coordinates x, y, and y. In a 3D space, it follows the same rule, which you just need to add 1 in the point. Next, let's move on. What is the relationships between homogeneous coordinates and geometric transformations? Well, homogeneous coordinates and geometric transformations are important in computer graphics because they allow for a unified and efficient way to represent and manipulate 2D and 3D shapes and images. In computer graphics, geometric transformations are used to manipulate the position, orientation, and scale of objects in a scene. These transformations include translation, rotation, scaling, and many more, which will be explained and highlighted later in this video by my teammates. By representing points and vectors using homogeneous coordinates, these transformations can be represented by a single matrix multiplication rather than having to perform multiple separate operations. Another benefit of using homogeneous coordinate in computer graphics is that it allows for a more elegant and efficient way to represent projective transformations, such as perspective projection in a 2D or 3D space. A projective transformations can be represented by a single matrix multiplication rather than we have to perform a multiple separate operations. Additionally, homogeneous coordinates also provide a way to represent lines and planes in a more compact and elegant way. It enables for more efficient algorithms to be used in computer graphics such as clipping, rasterization, and collision detection, and etc. In summary, the use of homogeneous coordinates and geometric transformations in computer graphics allows for a more elegant and efficient way to represent and manipulate 2D and 3D shapes and images, which is important for a wide range of applications such as computer-aided design, video games, and animations. That's all from me. Let's get to the next part.
Computer graphics are images that utilize matrices and vectors to generate the image, either in 2-dimensional or 3-dimensional. The idea behind is that instead of using pixels to generate image, computer graphics use a set of vectors or matrices to represent the image. Let us look at 2-dimensional first. For instance, to generate a square, you can use a set of vectors in R2 region as shown below. Sure, You can always transform the set of vectors into the homogeneous coordinate system without changing the final image produced. Now, for three-dimensional, the basic idea is still the same. The only difference is we have to use the vector in the R3 region to get the three-dimensional vector representation of the image. Furthermore, in generating more complex shapes, it might involve the use of vector function, which is just the entry of the vector as a function rather than a real value. For example, a sphere and a helix. Another important aspect of computer graphics is its animation. Unlike pixel graphics that had to generate thousands of frames to produce the animation, on the other hand, due to the nature of computer graphics as just a set of vector or matrices, it can employ different types of linear transformation or matrix transformation to produce the animation. These transformations are one of the core mechanics of any three-dimensional graphics. The change of matrix transformation allows the render of three-dimensional object on a two-dimensional monitor. The transformation of computer graphics includes scaling, rotation, reflection, shearing, and translation. All of these linear transformations can be represented by a transformation matrix, which renders them to be easily implemented in practical scenarios. The first type of transformation in computer graphics is scaling. Scaling is a transformation that results in an enlargement or diminishment of the original image. From the linear algebra aspect, it is done by transforming the vector of the original image to the another point by a scalar vector. The scaling transformation can be represented by a scaling matrix and its homogeneous form. The entries kx, ky, and kz in the scaling matrix represent the vectors by which the corresponding components of the vector are transformed. For example, the scaling matrix with kx equal to 3 and ky equal to 3 will result in a scaling transformation of 3 times larger than the original image. The second type of transformation in computer graphics is rotation. Rotation is the transformation associated with the spinning that occurs about an axis or point of rotation with the magnitude of theta. By convention, the rotation employs the right-hand rule, which is the rotation is in the counterclockwise direction. Although clockwise rotation still can be achieved by setting the transformation matrix to negative. In rotation, the final image is determined by two factors, which are the angle and the axis of rotation. The rotation transformation can also be represented by a rotation matrix. For example, the rotation about the x, y, and z axis can be represented by the matrices below. For other arbitrary axes of rotation, the rotational matrix is given by the matrix below. In practical sense, the rotation around the z-axis with an angle of 90 degrees can be done by multiplying the vector of the image by the rotation matrix as shown.
We move on to the next computer graphic transformation, which is reflection. So reflection is a transformation which produces a mirror image of an object. The mirror image can be either about x-axis or y-axis. The object is rotated by 180 degrees. So here are some of the reflection, which is about the x-axis, about the y-axis, and also about an axis perpendicular to xy plane and passing through the origin. Reflection about the x-axis. The object can be reflected about x-axis by using the following matrix, which indicate -1 only for the y component. So here, the values of y will be reversed, whereas the value of x will remain the same. The object will lie on another side of the x-axis, which is indicated in the graph here. So For reflection about the y-axis, the object can be reflected about y-axis by using the following transformation matrix, which is -1 for only the x component. So here the value of x will be reversed, whereas the value of y will remain the same. The object will lie on another side of the y-axis, as indicated in the graph here. So for reflection about an axis perpendicular to xy plane and passing through the origin, the object can be reflected by using the following transformation matrix, which indicate -1 for both x and y component. In this value of x and y both will be reversed. This is also called half revolution of the origin. As we can see, the transformation revolution about the origin. We move on to the next computer graphics transformation, which is shearing. Shearing deals with changing the shape and size of the 2D objects along x-axis and y-axis. It is similar to sliding the layers in one direction to change the shape of the 2D object. It is an ideal technique to change the shape of an existing object in a two-dimensional plane. In a two-dimensional plane, the object size can be changed along x direction as well as y direction. For x here, in x here, the y coordinates remain the same while the x coordinate changes. If Pxy is the point, then the new points will be P0, x0, y0, given as x0 equal to x plus the shearing factor of x times y, and y0 equals to y, which is remain the same. While the matrix form can be shown here, and we can see the shearing conduct here. We move on to the y shear. In y shear, the x coordinates remain the same, but the y coordinates changes. If Pxy is the point, then the new points will be P0, x0, y0, given as x0 equal to x, which is remain the same, and then y0 equal to y plus the shearing factor of y times x, with the matrix form as stated here. So here are the after the transformation, it will appear like this for y shear. And then for the xy shear, in xy shear, both the x and y coordinates changes. If Pxy is the point, then the new points will be P0, x0, y0, given as x0 equal to x plus shear factor of x times y, and y0 equals to y plus shear factor of y times x. So it will indicate as the matrix form right here, and the transformation will produce this image. We move on to the last computer graphics transformation, which is translation. Translation is a process where every point moves a constant distance in a specified direction. It can be described as a rigid motion. It can also be interpreted as the addition of a constant vector to every point, or as shifting the origin of the coordinate system. To translate a point from coordinate position xy to another point, we add algebraically the translation distance tx and ty to the original coordinate, right here. The translation pair tx and ty is called as shift vector. So here we can see the matrix for translation, which is here are the translation vector. And then translation is a movement of object without deformation. Every position or point is translated by the same amount. When the straight line is translated, then it will be drawn using endpoints. So that's all from us. Thank you.